All right, so let's go ahead and carry on with that. Let's go ahead and take a look at the next couple of questions, starting at number 5. Now, again, this is a newer concept. Composite functions sometimes are taught in Algebra 2, but last year, of course, they weren't. So this is kind of a new concept for a lot of us. So be patient with yourself if it doesn't come really, really fast. But in this particular situation, I'm asking you to find the answer for plugging 3 into G, get that answer, and then plug that answer in for F. So let's see, what was G of 3? Well, G of 3 would say 3 plus 1, which is 4, over 3 minus 2, which is, of course, 1. So it looks to me like G of 3 is the number 4. Now, I got to take that number and plug it into F, because G of 3 is, in fact, 4. So now I want to find out what is F of 4. So if I plug in 4 right there, I get 4 plus 2, and I get root 6. I'm actually done with that problem. That wasn't too bad. This problem's a little longer. It says, let's go find F of 7, get that answer, plug that answer into G, get that answer, and then plug that answer back into F. My goodness, look at all that work. So when I go to find F of 7, I'm going to get 7 plus 2, which is 9. That's a square root of 9, which of course is 3. Now I'm supposed to plug that into here. So now I'm finding F of G of 3. So if I found G of 3, that says go up here and do that. But notice I purposely tried to make that nice for you. We already know what G of 3 is. That was the number 4. We found it earlier. And so now instead of saying G of 3, I'm just going to say 4. So F of 4 is going to be right here. But again, I was being kind. F of 4, you could have just plugged it in right there or seen that you had it right there. And it was root 6. So kind of cool. Now, if you say h of g, that says let's take the function h, which is this entire function right here. That was 3x minus 2 all over x minus 5. And it says let's plug g into that. Oh my, if I plug g into that, that's going to create a little bit of a mess for us. I have x plus 1 over x minus 2. Now, clearly what I have now is I've got a fraction and a fraction, which is a little bit of an unpleasant story. So the trick that we do is we multiply the numerator and the denominator by the lowest common denominator that I see, which we usually refer to as a fraction buster. And the point of that is that when the x minus 2 hits this first term, these two pieces would cancel out. And I'm just left with the 3 and the x plus 1. But of course, if I continue and I multiply the x minus 2 over here, I'd have a negative 2x and a positive 4. Watch that distributive property. That does cause trouble sometimes. Now, of course, when these hit, the x minus 2's would cancel. The whole point of this was to make that fraction get better. But then we've got to remember to distribute here, and we have a negative 5x, and I have a positive 10. So putting it all together, it looks like my numerator has an x. My numerator has the 7 that is left. And in the denominator, there is a negative 4x and a positive 11. And that kind of finishes that up. Now, the tough part of that question for a lot of people is to find the domain of h of g. Well, if you look at the final answer, I can very clearly see that I can't have the number 11 fours. X cannot be 11 over 4 because if I did, I'd be dividing by 0. But the thing that we're supposed to do is we're supposed to look at not only the final answer, we're supposed to look at the inside function g itself. And if you were to look back at the inside function g itself has a problem that exists at the number 2. So I also cannot have x be 2. So that's kind of not too bad. Now, E says, let's find f of g. Now, f is this function right here. It was x plus 2. But of course, what I need to do to find out what goes right there is I need to stuff g in that hole, which is x plus 1 over x minus 2. Now, that's a little bit tricky because now I've got two things that I want to put together and look at it. And one's a fraction and one's not a fraction. So what I'm going to do is I'm going to create a common denominator. And that's not too bad. I have a common denominator of x minus 2. I have an x here and a 2x here for a total of 3 x's. I have a 1 here, and I look like I have a minus 4 here, so that looks like 1 take away 4 is negative 3. So Interestingly enough, I have variables on top and bottom. So that's kind of an interesting story because if the numerator and the denominator are both positive, I can take that square root because a positive over a positive is positive. Same thing if they're both negative, that's going to work too. But if we have one negative and one positive, that's a problem. So I've got to investigate a little bit. I know that the number 2 itself would be a bad number because that would put a 0 in the denominator and we can never divide by 0. But if I plugged in the number 1, it would produce a 0 on the top, and that's actually an okay thing to do because 0 divided by anything is 0, and I can do that. But if you try to move to the right of 2, let's see, if I tried a number like, say, 7, I'd get a positive numerator. 3 times 7 minus 3 is positive. 7 minus 2 is positive. So can I divide to positive? Well, that answer, of course, is yes. Same thing's going to happen over here because if I try on the left side, I'm going to get 2 negatives. But what's going to happen if you try a number like 1.5? You're going to find out that the top is positive, but the bottom is negative, and that's not okay. So the domain of this problem is everything from negative infinity to the number 1, and then everything from 2 to infinity. And you're going to notice that I could not use the 2 because that was the 0 in the denominator, but the 1 on top was okay. And we could not be in here because I would be taking the square root of a negative number. So that's kind of the end of problem 5. That was kind of a long question. We're going to kind of move into a little series of questions that are actually a little bit easier now. So when you look at this problem right here, you could see that if you could put your pen right here and spin your paper perfectly 180 degrees, the two graphs would be exactly the same. So this function is odd. And the same thing actually happens over here. Again, if you could spin your paper like this, I don't know if this is going to work on camera, but if I spin it like this, it's literally the exact same graph that I had when I started. So that's what makes a function an odd function. This one right here has very nice y-axis symmetry. See how the left and the right side look exactly the same, and that's what made it even. Remember, if f of negative x, which is the left side, is the same as the right side, that makes it even, whereas odd says if I tried to make x negative, it just flips the problem over. Now, I like this problem right here, but it's just messed up. You know, you try to spin it around, and it looks like it would be pretty good, but if you tried to spin it around, this is a little bit lower than this is high. They just don't quite match up. It's close, but this one is a story that is neither odd nor even. It was close to having that kind of symmetry, but not quite sufficient. All right, so moving to number 7, which is kind of where I think I'm going to end this particular video. We'll just ask about whether it's odd or even, but this time we're not going to be using a picture. We're going to be using the formal definition. So the formal definition says replace x with negative x. And we're going to try to find out, do we in fact, by doing that, come back to the same exact question as where it began? So if you square negative x right here, negative x times negative x is positive x squared. So the numerator looks like my original problem. And if I took negative x and squared it and then multiplied it by a negative, I had 1, 2, 3 negatives. So that's 3 minus x squared, which is exactly j of x. So notice that I tried to plug in negative x and I got the same thing back as the original, and that matches the definition of an even function. Now in B, when I tried j of negative x, in the numerator, something strange kind of happens. But in the denominator, I think you can probably see that if I take a negative x times a negative x, so you're going to notice that the denominator was completely the same as the original story. But the numerator has 3 negatives here, and it has 2 negatives here. And so really what we could do in this story is we could factor a negative out of the numerator alone. And a lot of people don't think you can do that, but you can. You can factor something out of the top and leave the bottom as it is. But what I can see right now is this is the opposite of that original function. So this is showing that this is the opposite of j of x, which matches the definition of odd, because notice we just said j of negative x started it, and we found that that was equal to negative j of x. That's our very definition. Now, for C is kind of an interesting problem. You know, I don't really know exactly how you would want to do that, but this is actually not going to be odd or even, and it's very, very easy to try, because if we just did an example, we could blow it out of the water. Let's see what happens if we tried 2 and negative 2. Well, if I plugged in 2, this would be e to the third. Very simple number, e times e times e, whatever that is. Whereas if I did, which I could even use my calculator to show you that e to the third is 20.08. You may not be familiar with e, but we'll learn about it over time. And if I try negative 2, this was e to the negative 1, which is like 1 over e. Well, you can see those are definitely not the same. They're not the opposite of each other. That's neither. If it's not perfect, it's neither. And notice that I could get away with just doing an example, because although you cannot prove with an example, you can disprove. And my last example is this one, k of negative x. I'm going to replace all the x's with negative x's. And in the denominator, notice I have 5 negatives and I've got 1 negative. And what's a little interesting is that a negative inside of an absolute value like that doesn't do a darn thing. So I could kind of eliminate that. And so you might have noticed that this is, in fact, the same as my original problem, which leads me to believe that this is the opposite of k of x, which leads me to the conclusion that this is an odd function. So if you were to graph this one, you would see origin symmetry. If you would graph this one, you would also see origin symmetry. And if you graph this one, you would see y-axis symmetry. So that kind of concludes the second video. I'll be uploading another one to go through the final questions, and I hope that's helpful.